Hello, everyone. Welcome to our tutorial about scaling out NLP applications to more than 100 languages. First, let me introduce the presenters and the content of this tutorial. My name is Daxin Jiang, and the other three presenters are Linjun Shou, Xiubo Geng, and Ming Gong. So all of us are from the NLP group of Microsoft Software Technology Center at Asia, or STCA for short. In the first part of this tutorial, I will give an introduction of language scaling for NLP applications. We will start with several concrete examples of NLP applications in Microsoft products and services, and then we will describe the problem setting for language scaling. Although there are many NLP applications and they may look quite different, we will propose a systematic categorization so that the applications sharing the same NLP task will be grouped into the same category. The benefit of such a categorization is to facilitate generalization. That means we can generalize similar approaches to different applications as long as they belong to the same category. At the end of this introduction part, we will summarize the common challenges for language scaling and briefly describe the major approaches to address those challenges. Then the major content of this tutorial is in the second part, where we present more technical details for language scaling. Since NLP is such a broad area, we cannot cover all the applications. So here we just follow our categorization of NLP applications and select one representative application for one type of NLP tasks. So these applications include natural language inference, information retrieval, and machine reading comprehension. So my colleagues Linjun, Xiubo, and Ming will present these topics. Finally, in the last part of this tutorial, it will be my turn again. So I will propose several future directions for language scaling. Okay, so everything needs to have a motivation, right? So before we jump into the technical part, I can come up with the motivation for language scaling from several perspectives. First is from society and humanity perspective. We believe language scaling is invaluable to the advance of social welfare. So here I just lifted the content from the SIL website. I think it perfectly explains why language matters. For example, to eradicate extreme poverty and hunger, to achieve universal primary education, to promote gender equality and empower women, and many more. The importance of language scaling can also be viewed from industry perspective. So here, please allow me to quote the mission statement of Microsoft as an example. So the mission statement says to empower every person and every organization on the planet to achieve more. So we can read the needs for language scaling from this statement. In fact, natural language processing has been widely adopted in various Microsoft products and services, including Bing, Azure, Office 365, and so on. So in the following, let's look at several examples of those applications. So as the first example, speller is a key component in Bing and Office. For example, in Bing traffic, around 15% of user queries contain spelling errors. So here are some examples for spelling correction for different languages. Spelling correction for 100 languages actually raises a very interesting challenge. That is, we need to find a balance between scalability versus specificity. Intuitively, when we scale out to many languages, we should consider more about the common features among different languages, because otherwise we simply cannot scale out. For spelling correction, we do have some common features like character insertion, deletion, substitution, and transposition. However, we also observe that if we only focus on common features but completely ignore language-specific features, the quality of our model will never be good enough. So one example is the Japanese speller. We know that there are 4 different types of scripts in Japanese. including kanji, hiragana, katakana, and romaji. And there are two different types of input methods. On PC, people usually use romaji, while on mobile, people often use kana. So if we don't handle these language-specific features, the speller performance will not be competitive for Japanese. For example, for these two Japanese strings, if we compare the surface characters, they look completely different, right? However, if we consider the input methods, then no matter kana or romaji, they are actually different within just one keystroke. So in speller design, we need to collect language-specific training data. And at the same time, we need to make the trade-off between scalability and the specificity to meet the highest ROI. That is return over invest. The second example is Bing search relevance. As we can see from these examples, currently the Bing search engine provides web results in more than 100 different languages. And now the web ranker in Bing has been powered by deep learning models. So the challenge here is about efficiency. We know that a multilingual deep ranking model often contains hundreds of millions or even billions of parameters. So this is a huge model. Then on the other side, the web index contains hundreds of billions of documents. So this is a huge index. And for each query, we need to rank the top 10 most relevant documents from the huge index by the huge model with a very limited budget, usually several hundred milliseconds. Therefore, we have to design smart ways to improve the efficiency while still keeping the relevance power of the big model. The third example is from Outlook. Currently, in Outlook, if the user's response to the incoming emails only involve generic acknowledgement, greetings, confirmations, and so on, the service can automatically suggest short and relevant replies as shown in these examples. So users can simply click on these suggested replies instead of typing these characters. So this feature can save the user's time. Suggested reply in Outlook has also been available in multiple languages, as we can see from these examples. And similar to web search, one challenge behind this application is also to compress the huge deep learning models and serve them online with high efficiency. But another challenge for suggested reply is data privacy issue. So currently, Outlook data for different countries are stored in their corresponding data centers. According to the compliance restrictions, those data cannot be moved out of the data center. However, we need to train a universal model to serve all languages because users in the same region often speak multiple languages. If we only use the data from a single data center to train a universal model, the data may not be sufficient, and we actually wasted data from other data centers. Unfortunately, due to the compliance restriction, we cannot mix the data from all the data centers. So an interesting challenge here is how to fully leverage the data from all the data centers, but without breaking the privacy constraints. The fourth and last example is from Microsoft Teams voice assistant. For example, when a user speaks the sentence to Teams, "Join my next meeting," the system will conduct a semantic parsing to this sentence. To be more specific, it will recognize the domain for this sentence is calendar, and the user intent is connect to meeting. It will further extract the term next to interpret the start time for the meeting. So after the semantic parsing, the results will trigger the Teams action to join the next meeting for the user. And now Teams has supported a large number of domains for various languages. In order to support a large number of domains and a large number of languages, we need to find large amounts of training data. However, as we will explain in later slides, it is usually a big challenge to collect the training data, especially in non-English languages. Moreover, to support semantic parsing for each domain and for each language, we usually need to build a domain classification model, an intent detection model, and a slot tagging model. In practice, we have hundreds of domains and more than 100 languages. So the total number of models will be very large. Such a large number of models present big challenges for model training, deployment, and maintenance. So in the industrial applications, we need to handle both challenges. One is the lack of training data, and the other is to handle a large number of models. Okay, all the previous applications and challenges are not only interesting to industry, they also attract intensive interest from the research community as well. So if we search for multilingual, cross-lingual, or bilingual in the ACL answer log, which includes the ACL and the EM NLP conferences, we can see the number of papers has been increasing very fast. And in particular, in the past 2 years, it has become a very hot topic. Okay, since language really matters, now let's look at the problem description for language scaling. But given an NLP application, such as the examples we demonstrated in the previous slides, in practice, we usually have relatively rich English training data. And oftentimes from those English training data, we may result in a well-trained English model. Then our task is to scale out the English model to more than 100 languages. And there are two requirements for language scaling. One is effectiveness, meaning that we have to guarantee the model quality to meet certain criteria. For example, the shipping criteria in terms of precision and recall for our products and services. And the other requirement is efficiency. That means when we handle so many languages, we have to reduce the costs in both money and time as much as possible. So the previous problem description is clear when the input is a single text. However, when the task involves two inputs, there might be some ambiguity. For example, in web relevance, one input is user query and the other input is web documents. So in previous problem setting, we have English training data where both queries and documents are in English. And then we transfer to other languages. For example, both queries and documents are in Chinese. But there could be a related problem setting where the queries are in one language, for example, in Chinese, and the documents are in another language, let's say in German. This problem also involves different languages. So to distinguish these two different settings, we call the first setting language transfer and the second setting cross-lingual. However, in the following, we will not explicitly distinguish these two settings because both of these two settings need the same multilingual representation and cross-lingual alignment. So we just need to register there exist these two slightly different settings, but the approaches are basically in common. After we introduce the problem setting, we further propose a categorization of various NLP tasks. As mentioned before, the reason for this categorization is to facilitate generalization. That means we may apply similar approaches to all the various applications belonging to the same category. So at the highest level, the NLP tasks can be divided into NLU and NLG, which means natural language understanding and natural language generation, respectively. Then the NLU tasks can be further divided into classification and sequence labeling. In case some audience are not very familiar with these tasks in the following, I will use some examples to explain the input and output of these tasks. Okay, so the first task is text classification. And depending on the user input, text classification has two scenarios. The first scenario is that the input is just a single text. For example, when the user raises a query, what's the average rain of Beijing in summer to Bing search engine? One classification task is to tell the domain for this query. For example, whether this query belongs to the domain of recipe, weather, celebrity, or some other domains. And similarly, another example of classification task is to assign an intent label to this query among all the predefined user intents. such as check weather, check history statistics, and so on. And the second scenario for text classification involves two input texts instead of one. Then the classification task is often regarded to the relation between these two texts. As one example, given two queries, we may want to know whether they are paraphrased to each other. And a special case in this category is information retrieval. For example, in web search, one input is user query, and the other is web documents. And the task is to rank the documents based on their relevance to the query. Although the ranking task is concerned about the relative order of the documents with respect to the query, here we still consider it as a special case for classification, because essentially the task is still to predict the relevance score between a document and a query. Similar to text classification, the task of sequence labeling can also be divided into two scenarios, depending on the input. So for single text input, one example for sequence labeling is named entity recognition, or NER for short. So traditional NER only considers person, organization, and locations as entities. But depending on the requirement of applications, we can expand the set of target entities. So here's one example to trigger a flight status answer card on a Bing search engine. Given a user query, we need to label various entities, also called slots, such as the departure airport, arrival airport, airline company, and so on. So this task is also called slot tagging. So both NER and the slot tagging belong to the category of a single text sequence labeling. For text pair, the example is machine reading comprehension, where for each instance, we have a question and a passage. Then the problem is to label the answer span with respect to the given query within the given passage. So here is one example from Bing. If you ask what's the date for the web conference 2021, the search engine will highlight the answer to this question, which is April 19 to April 23rd, 2021. And for text generation, the subcategories can be divided based on the granularity of input. For example, whether they are at the token level or sentence level. So for token level generation, the examples are spelling correction, and sentence auto-completion. So here are some real cases for spelling correction from Bing search engine, as well as some examples for sentence auto-completion from Microsoft Word. And there are also many applications for sentence level generation, such as machine translation and response generation in conversations. Here are some concrete examples. Okay, so based on the previous categorization of NLP tasks, we will look into individual categories with representative applications in the later part of this tutorial. But before that, we would like to summarize several common challenges for language scaling, which are faced by all the NLP tasks. So after we present the common challenges, we will also give an overall picture for the approaches that address these challenges. In this introduction part, we will not explain too much detail for these approaches. Instead, the purpose is to help the audience to understand the global picture, so that when we deep dive into the individual techniques in the later part, we will be clear where we are and what the relation is with other approaches. Okay, now let's look at the common challenges for language scaling. The first one is lack of training data. So for English, the size of human labeled data is usually at the magnitude of millions. Apparently, it is unrealistic to label so much data for each language. And please recall that in previous slides, we mentioned several challenges for some example applications, such as the language-specific features for Japanese speller, data privacy issues in Outlook suggested reply, and the difficulty to support many domains for Teams voice assistant. In fact, all these issues are related to the challenge of training data collection. And in the following part, how to address this data challenge is also the major focus of this tutorial. Then the second challenge is how to deal with a large number of models. As we demonstrated in the application of Teams voice assistant in the previous slide, the large number of domains times the large number of languages will result in a large number of models. The challenge here is that if we have a lot of models, the cost for model building, serving, and maintenance will be very large. So to solve this challenge, several studies proposed multitask learning and adapters. So the idea of multitask learning is to share the model parameters for different domains, applications, and languages. Therefore, the number of models can be greatly reduced. However, it is difficult to optimize the shared parameters for individual tasks. Right? So this actually motivates the idea of adapters, where the parameters are decomposed into two parts. A majority part of the parameters will still be shared, but at the same time, a small part of the parameters will be grouped into the so-called adapters, and they are fine-tuned for specific tasks. In this way, it keeps a balance between the maintenance cost for models and the flexibility for individual tasks. Okay. So the third challenge is model size and latency. As we introduced in the application of web relevance, a deep learning model often has hundreds of millions or even billions of parameters. So these models are too heavy to be served online. And in practice, there have been various efforts to mitigate this challenge. For example, hardware acceleration, computation library optimization, as well as all kinds of model compression methods. Okay. So in this tutorial, we'll not cover the approaches for all these three challenges. Instead, we'll mainly focus on the first challenge, that is, how can we scale out to 100 languages with a few or even zero training data in the target languages. In order to tackle the challenge of small or zero training data in target languages, the basic idea is to transfer the knowledge from the source language to the target language. And in general, there are two transfer approaches. One is called model transfer, and the other is called data transfer. So let's first discuss the model transfer approach. The first step in model transfer is to build a cross-lingual model. The purpose of a cross-lingual model is to learn the alignment between the representations for different languages, which is illustrated by these two figures. The upper figure represents the distribution of different languages before the alignment. We can see that they are independently distributed and there is no relation between the words in different languages. And the lower figure shows the effect after alignment. The similar words in two languages, such as gato in German and cat in English, which have similar meaning, are mapped close to each other in the aligned space. After we have a cross-lingual model, the second step is called fine-tuning. That means we use English training data to continuously train the cross-lingual model. So since the English training data is aimed at a particular task, the model after fine-tuning will perform well on that targeted task. And one thing to call out here is that the cross-lingual model has already aligned different languages into a common space. Therefore, the features used by the fine-tuned model is language agnostic. In the last step, which is the test stage for fine-tuned model, given one test instance in a different language, we apply the same cross-lingual model to map the target language into language agnostic representation. Then the fine-tuned model will not distinguish from which original language the input is from. Instead, we'll generate the results uniformly for all languages. So in a short summary, the model transfer approach consists of 3 steps. First, we train a cross-lingual model to align different languages. Second, we use the English training data to fine-tune the model. And lastly, we apply the same cross-lingual model to generate language-agnostic features and fit into the fine-tuned model to derive the final result. Among all these three steps, the most critical one is the first step, where we train a cross-lingual model to align different languages. And that's also the reason why this approach is called model transfer. So in the following, let's have a review of various cross-lingual models. So as we illustrated in the previous slide, the goal of cross-lingual models is to represent different languages in a shared vector space, such that the texts with similar meaning are aligned close to each other, no matter in which language they're expressed. At a high level, we distinguish two types of cross-lingual models, depending on how the languages are represented. The first type represents languages by word embedding, so it is called cross-lingual word embedding. And the second type represents language by contextual embedding. Accordingly, it is named as a cross-lingual contextual embedding. So in the following, let's look at more details of these two types one by one. For cross-lingual word embedding, at the first level, it can be divided into mapping-based methods and joint learning methods. For mapping-based method, it usually has two steps, as indicated by the numbers 1 and 2 here. So the first step is to learn word embedding for each individual language independently. And then the second step is to learn a mapping matrix between two language embeddings. So in this formula, XS and XT, in the first part, denote the word embedding matrices for the source and target languages respectively. And L is the loss function for learning the word embeddings. Then in the second part, omega is the loss for the mapping matrix W that aligns XS and XT. In the joint learning method, the word embedding loss and the alignment loss are optimized at the same time. That means both languages share the same vector space so that the words with similar meaning in different languages are mapped as close as possible in this shared vector space. It's actually quite obvious to differentiate these two types of methods. We just need to check when the language alignment happens. So if the alignment happens after the word embedding, it is a mapping-based method. Otherwise, if the alignment happens at the same time with the word embedding, then it is a joint learning method. Both mapping-based methods and joint learning methods can be further divided into smaller categories. But in this tutorial, we'll not cover the details, since Radar et al. Have already gave a great tutorial and a survey paper for these various methods. So we refer the audience to these materials. The word embedding learns the encoding for individual words. Although it is lightweight and effective, a big limitation is that it can hardly address the issue of word ambiguity. We know that many words have multiple senses, right? So in order to accurately capture the meaning of words in sentences, we need to take context information into consideration. So that is the motivation for contextual embedding models. And this figure summarizes the various approaches to cross-lingual contextual embedding. Similar with cross-lingual word embedding, at the highest level, cross-lingual contextual embedding methods can also be divided based on the time when the alignment between languages happens. If the alignment happens simultaneously with the learning of contextual embeddings, then it is a joint learning method. Otherwise, if the alignment happens after the contextual embedding for individual languages, then it is a retrofitting method. For these two types of methods, the mainstream for cross-lingual contextual embedding is the joint learning methods. And there are only a few works belonging to the retrofitting methods. So let's first take a closer look at joint learning methods. Joint learning methods can be further divided into two subtypes, depending on whether they need parallel data or not for alignment. For the methods which need parallel data, we summarize the three major ideas, namely neural machine translation-based approach, dual encoder, and a language model-based approach. In this introduction part, we'll pick up one example for each approach to briefly introduce the major idea at a high level. And we'll also highlight the major differences among these various methods. But we'll leave the technical details and the more related works for each of these approaches in the second part of this tutorial when we deep dive into concrete applications. A representative work of neural machine translation-based method is by Artegia and Schwenk. So the basic idea is to apply an encoder-decoder architecture for machine translation. And to be more specific, the encoder part takes in a sentence in the source language and encode it into a sentence embedding vector. Then based on this vector, the decoder part will generate the translation of the input sentence into the corresponding target language. So this is the standard sequence-to-sequence neural machine translation architecture. Then you might wonder why this neural machine translation architecture can be used to train cross-lingual models. The idea is to apply many-to-many translation. To be more specific, there are multiple source languages at the input side, but there is no indicator to distinguish the input languages. In other words, all the information that the decoder can see is just the sentence embedding vector generated by the encoder. Therefore, this setup implicitly enforces all the input languages to have a uniform encoding. Okay, so this is the basic idea for NMT-based method. And there are more variations for this idea. We will introduce more details in the second part. Different from the previous NMT-based approach, the dual encoder approach adds explicit constraint for language alignment. So here, let's look at work from Guo et al. As a representative to explain the idea. Suppose X and Y are two sentences in two different languages. So each of them goes through a stack of hidden layers and gets an encoding vector, let's say U and V respectively. Then there is a scoring function phi xy to evaluate the similarity of X and Y. For example, in Guo et al.'s paper, they also simply applied the dot product of U and V as the scoring function. And in order to train this cross-lingual embedding, we can leverage the parallel data as the training data. So if Y is the translation for X, then the score for phi xy is high. Otherwise, the score is low. So in this way, the embeddings of different languages are aligned to the same space. Again, there are several follow-up works based on this dual encoder idea. We will present more details in the second part. The third type of contextual cross-lingual models usually employ transformers to learn language models. The major difference between this approach with the previous two approaches lies in the granularity of cross-lingual units. So in the previous two approaches, the models aggregate the word representations into sentences, and the unit to transfer across the languages is a sentence embedding. However, in transformer-based language model approach, we can find cross-lingual representation at both sentence level and the token level. So for now, let's just be aware of this key difference, and we'll describe the technical details in the second part of this tutorial. So the common point for the previous three approaches is that they all apply parallel data for language alignment. Right? However, in practice, it is usually expensive to collect parallel data, especially for resource-low languages. There may not be parallel data available at all. So some recent works have shown that we may not necessarily need parallel data to learn cross-lingual models. In the following, let's look at some examples. So multilingual BERT, also called MBERT, is probably the first work that does not use parallel data to learn cross-lingual representations. In fact, the multilingual BERT model shares the same architecture and the training scheme with the monolingual BERT model. The major differences are in the training data and the vocabulary. So for monolingual BERT, the vocabulary contains English words only, and the model is trained by pure English data. In contrast, the multilingual BERT is trained by the Wikipedia pages in 104 languages, and the vocabulary contains 110,000 word piece tokens covering all the 104 languages. The amazing thing here is that although the whole training process for multilingual BERT does not carry out any explicit or implicit alignment across languages, it still shows very good cross-lingual capability. So many works explored why MBERT has cross-lingual effectiveness. Earlier works attributed the cross-lingual capability to vocabulary overlap among different languages. For example, the Latin family languages share many cognate words. Even for distant languages such as Chinese, the text may still contain some English words, such as CPU, GDP, and so on. So these shared words act as the anchors to align different languages. However, some later works disclosed more evidence that shared words are not the reason, or at least not the only reason for cross-lingual capability. One study showed that MBERT still has cross-lingual effectiveness even when there is a zero vocabulary overlap. Therefore, some studies postulate that the cross-lingual capability may come from the common structure in different languages. For example, many languages share the subject, verb, object, word order, and the distribution for the most frequent words in different languages could be similar to each other. If you are interested in this topic, I listed several related works for your reference. So multilingual BERT is a language encoder. So it is mainly used for language understanding tasks. Correspondingly, for language generation tasks, an example model that does not use parallel data is called multilingual BART. So MBART and MBERT is different in only one character. So please don't confuse these two models. MBART is for language generation, while MBERT is for language understanding. And the idea of MBART is actually very similar with that of MBERT. So the multilingual BART shares the same model architecture and the training scheme with the monolingual version. And the differences are mainly in training data and the vocabulary. The monolingual version contains only English data and English vocabulary, while the multilingual version contains mixed language data and a comprehensive vocabulary to cover all the languages. Okay, all the previous methods are joint learning method in the sense that the cross-lingual alignment is learned at the same time with contextual embedding. In contrast, the retrofitting methods build the cross-lingual alignment or enhance the alignment after the learning of a contextual embedding. So let's take a look at the two representative methods. The first method is called contextual token mapping. The idea is very similar with the previous mapping-based cross-lingual word embedding. We know that for word embedding, each word in a language has a fixed embedding, which does not change with the context of the word. Then in a mapping-based cross-lingual approach, we learn a matrix W, which maps the word embedding for one language to another language, so that the embedding vectors of the aligned words have the minimum distances. And moreover, to make the mapping more robust, it is often helpful to regularize the mapping matrix W to be orthogonal matrix. The major difference between a contextual token mapping and a static word mapping is the sampling methods for aligned words. So in static word mapping, the word pairs are sampled from bilingual dictionaries without considering the context of the words. But in contextual token mapping, the vectors for xi and yi are sampled from the occurrences of the words in the parallel sentences. Therefore, this sampling approach actually takes the context information into consideration. So each token vector only represents a single non-ambiguous sense of the word. Therefore, the mapping is expected to be more accurate. And the second retrofitting method, which is called model fine-tuning, does not learn explicit mapping matrix W between two languages. Instead, it uses the parallel data to fine-tune the parameters of multilingual BERT so that the aligned words in the parallel sentences become closer to each other. So this upper figure shows the effect of a base multilingual BERT, and the lower figure shows the effect after fine-tuning. So we can see that aligned words are dragged closer to each other in the lower figure. And this idea is formulated by the loss function on the right side. In this loss function, F is the MBERT model and C is a parallel corpus. So for each pair of parallel sentences S and T in the corpus C, we want to minimize the distance between the representations for the aligned words I and J in the parallel sentences S and T, respectively. And back to these two figures, for the base MBERT model, when no minimization process is applied, the distances between aligned words are still pretty large. Then through this minimization process, also called fine-tuning process, the distances become much smaller. So one detail here is that in order to avoid a trivial alignment, for example, the encoding function always outputs constant vectors, the authors also added a regularization factor, which requires the change to the original encoding from the base MBERT is also minimized. Okay, so this is the whole picture for the various cross-lingual models. In this tutorial, we mainly focus on the contextual embedding models, which is the right subtree of the root node. And in previous slides, we briefly introduced the major ideas of various models, and we highlight the common and the different points for these methods. Then in the second part of this tutorial, we'll come back with more details for these models. We'll also demonstrate how these models are applied to specific applications. For example, when Linjun talks about natural language inference, he will cover language model-based methods, either with and without parallel data. And when Shubo presents cross-lingual information retrieval tasks, she will elaborate more variations for NMT-based methods and dual encoders. So in addition to the model transfer approach, another approach to language scaling is data transfer. Then you might want to say, given that we already have so many cross-lingual models, why we still need a data transfer approach? The reason is that languages are extremely complex, and there exist huge differences between different languages. For example, they may have very different vocabularies, morphological rules, syntactic structures, and so on. So such complex difference may not be fully captured and well aligned by the cross-lingual models. In practice, even we apply the cross-lingual models, we often observe big gaps in the model performance on English test data versus on other languages. Therefore, we may consider data transfer as a complementary approach to model transfer approach. So in data transfer approach, the central idea is to transcribe the knowledge either in the source training data or in the source model into the training data of the target languages. And as we will discuss in the later slides, there are 4 types of methods to transcribe the knowledge, including machine translation, semi-supervised learning, weakly supervised learning, and the data generation. So sometimes the transcription process may also leverage some auxiliary data, such as the unlabeled target data, user feedback data, and entity data. So after we derive the training data in the target languages, then the remaining step is straightforward. That is, we simply use the training data in target language to train the target models. In fact, the model transfer approach and the data transfer approach are not exclusive. They are often combined in practice. So this is the model transfer process as we described before. Right? So we result in this fine-tuned model that takes in language agnostic features. So after this model transfer, we can further apply the data transfer methods, which will derive the pseudo training data in target languages. Then in the next step, we continue training the fine-tuned model with this pseudo training data and derive an enhanced model. Finally, this enhanced model is used to handle the test data in the target languages. So this is how we combine the model transfer and the data transfer approaches in practice. Now let's take a look at various data transfer methods, starting with machine translation. So for the purpose of language scaling, there are two directions for machine translation. So one direction is to translate the training data in source language into target language. This direction is called translate on train. For example, suppose the source data is in English and the target language is Hindi. So we can apply machine translator to translate the English training data into Hindi training data. And after translation, we usually need to further apply the sentence alignment methods to derive the labels from the source instances to the translated instances. And in the third step, we use the translated Hindi data with the labels to train Hindi models. So this process follows the standard flow we introduced in the previous slides. And please note that in this process, the machine translation, sentence alignment, and model training steps are all carried out at the offline stage. Then at the online stage, we directly use this Hindi model to do the inference. So in fact, for machine translation methods, there exists another translation direction, which is totally opposite with the previous flow. So this opposite direction is called translate on test. We also introduced this direction for your reference. As the name suggests, translate on test means that the machine translation happens at the online stage, and the translation direction is from the target language to the source language. So again, let's suppose the target language is Hindi and the source language is English, and we already have an English model trained from the English training data. Okay, then given a Hindi test case, we'll apply machine translation online to translate it into an English test case. And then we apply this English model on this translated English test case to get the result. And finally, we still need to further align the English test case with the Hindi test case to derive the label on the original Hindi test case. So this is the flow for translate on test. In practice, most applications prefer translate on train rather than translate on test. The reason is that translate on test need extra time for machine translation and sentence alignment at the online inference stage. Right? So for many online services, latency is very critical for user experience. Therefore, we usually adopt translate on train approach to reduce the online latency as much as possible. So the machine translation approach assumes there is a translator between the source language and the target language. However, for some target languages, the machine translator may not be available. In such cases, we may consider whether it is still possible to collect unlabeled data in target languages. For example, for the task of machine reading comprehension, we can easily collect large amounts of queries and passages in 100 languages from the Bing search engine. So once the unlabeled data in the target language is available, we can carry out semi-supervised learning. So in the first step, we can leverage the previous model transfer approach and derive an initial model. Then in the second step, we'll apply this initial model to the unlabeled data in the target language. And consequently, for each unlabeled instance, we now have the labeling result, which is generated by the initial model. That means the unlabeled data becomes labeled data now. So in the next step, we use this labeled data to retrain the initial model. And this process can be iterated for several rounds. Intuitively, if the initial model can derive reasonable labeling results, then after we apply it to convert the unlabeled data into labeled data, such extra training thoughts can help to improve the model quality. Then in the next round, the model with improved quality can further generate even better labeling results. And this iteration gradually improves the model performance round by round. So in practice, in order to guide the iteration towards better labeling results and better models, we may adopt some techniques such as self-training, model ensemble, and reinforcement learning. So we'll also cover more details for these techniques when we talk about machine reading comprehension in the second part of this tutorial. So in addition to unlabeled data, sometimes it may also be possible to collect various auxiliary data to help with the target tasks. So this auxiliary data may provide indirect signals to supervise the learning process. That's why they are called weakly supervised learning methods. And in the following, let's look at 2 examples to illustrate this idea. So one example is question answering for Bing. Let's still reuse the previous example. When the user asks the question, what is the date for the web conference 2021? The Bing search engine will provide this passage and highlight the answer at the top position in the search result page. Then how do we know whether this passage is relevant to the user question or not? So from the search engine logs, we can collect rich user behaviors. For example, how long the user dwells on the search result page, whether the user clicks on the URL in the question answering block, whether the user reformulates the query, whether the user clicks on web documents outside the question answering block, and so on. Although each single user behavior is only a weak signal for the relevance of the passage, when they are combined in a machine learning model, the predicted prediction accuracy becomes pretty high. And in our empirical study, we find that the users all over the world have similar behavior patterns. That means this method is generally applicable to all languages. Therefore, in this way, we can cheaply collect very large amounts of training data for all languages. So this is one example. We collect user feedback as a weakly supervision signal. Another example also comes from question answering scenario for Bing. So after we provide the relevant passage to the user question, we need to further highlight the answer span in the passage. For example, in this example, the highlighted span is April 19 to April 23rd, 2021. So this task is called machine reading comprehension, or MRC for short. One challenge for MRC is to accurately detect the boundary of the answer span. So here are 2 examples. So in the upper example, the ground truth is King David, but the predicted answer includes some extra irrelevant words. Then in the lower example, the ground truth is 50 to 100 milligrams, but the predicted answer only has 100 milligrams, so it misses some useful words. In order to address this boundary detection challenge, one idea is to use a large volume of entity data to pre-train the MRC model. In other words, we can mask the whole entities in the sentences and let the model recover the full entity span. Since many answer spans are constituted by entities, such a pre-training process can effectively improve the accuracy of boundary detection. So in this example, the entity data serves as the auxiliary data, which provides weak supervision signals to the MRC model. And since the entity data can be automatically mined from the web, this method is also generally applicable to all languages. The last commonly used data transfer method is data generation. So the idea is very straightforward. Since we lack the training data in the target languages, we try to synthesize some training data to approximate the real data. Then the problem becomes how to build a cross-lingual data generator. In practice, different approaches have different forms of training instances. So the data generators will also be very different accordingly. Here, I will just use one example task to illustrate the idea. To be more specific, the example is a natural language understanding, or NLU for short. So the task of natural language understanding predicts the intent of user input, and at the same time, it will also labels the important slots in the input. For example, when the user inputs PVG to SFO Delta flight status, the intent is to check flight status, and there are 3 slots to be labeled, as shown in this figure. This NLU task often serves as a key component in task-oriented dialogues. So in the terminology of dialogues, the intent plus the slots are often called a dialogue act. So we can also say that the NLU task is to derive a dialogue act given user input. Then, in order to generate the synthetic training data for this NLU task, the input is the dialogue act, and the output will be a sentence corresponding to the dialogue act. So this task is called NLG, Natural Language Generation. So now we have both NLU task and NLG task at hand. And these 2 tasks are highly correlated. So let us review again their relation in order not to confuse them. Please note that the NLU task is our primary problem. So the input is the user sentence and output is a dialogue act. Then in order to generate the training data for the NLU task, we need to introduce the reverse problem, which is NLG. And in this NLG task, the input is a dialogue act, and the output is a synthesized user input. Once we have an NLG model, we can apply it to generate many pairs of user input and a dialogue act. And these pairs are exactly the training instances for the NLU task. So I hope that the relation between NLU and NLG is clear now. So now the problem is how can we build an NLG model? One example is Peng et al.'s work. The authors apply a GPT model to fulfill this task. You can find the details in this paper if you are interested in the generation process. And some works consider the NLU and NLG tasks as a pair of a dual problem, where the input of one task is exactly the output of another task, and vice versa. So they develop dual learning methods to enhance the performance of both tasks. Again, I will skip the details, but list the reference paper here. Okay, so in previous slides, we introduced the 4 different types of data transfer methods. Here, let us have a brief summary. So please remember that the central idea of data transfer is to produce pseudo-training data, which is the pair of X and Y in the target language, where X is the set of training instances and Y is the corresponding labels. So we can compare the different methods through the perspectives of how X and Y are produced. First, for machine translation, we translate the training data from the source language to the target language. So the data instances are derived from machine translation, and the labels are derived from the alignment between the translated pairs. Then for semi-supervised learning, we leverage the unlabeled data in the target language. So the data instances are real data. And in order to generate the labels, we can apply an initial model, which is derived from the model transfer approach to the real unlabeled data. And in practice, we often iterate the process for several rounds and improve the model quality and the label quality in turns. Next, for weakly supervised learning, we also use the real unlabeled data in the target language as the training instances. In order to derive the labels, we leverage some auxiliary data and extract weak supervision signals. Some examples of auxiliary data could be user feedback or entity data. Then the last method is data generation. So in this method, we usually generate the labels first using some heuristic rules, and then we will build a data generator to synthesize the training instances based on the generated labels. Okay, so far we have finished the introduction part. So in this part, we looked at several NLP examples, described the problem of language scaling, proposed a categorization for NLP tasks, and also discussed at a high level the challenges and the major approaches to language scaling. Then in the next part, let's drill down into 3 concrete applications and discuss more technical details. First, my colleague Lin Jun will talk about natural language inference.
Thanks, Daxin, for the introduction. My name is Lin Jun So, data scientist from Microsoft. Next, I'll take cross-lingual natural language inference as one application for language scaling. Referring to the categorization of NLP tasks in Daxin's slides, natural language inference belongs to text pair classification of NLU tasks. I'll give the details task definition in later slides. First, what is cross-lingual natural language inference? To be specific, given a premise and hypothesis, natural language inference task aims to predict the relationship between these 2 sentences, such as entailment, neutral, or contradiction. Table 1 shows some example cases of NLI tasks. Take the English case example. The premise is you don't have to stay there, and the hypothesis you can leave. So we can see that the relationship between these 2 sentences is the entailment, while there are also other cases where the relationship can be neutral or it can be contradiction. While for cross-lingual setting, the task requires a model to transfer from English to other languages. So in terms of training data, the model is able to train on English training data only, then the model is able to transfer to other languages. In terms of benchmark datasets, XNI is a commonly used benchmark dataset for cross-lingual natural language inference task, which is first published in Mrc 2018. Okay, in these slides, let's talk about the approaches. We could categorize the approaches for cross-lingual natural language inference into 2 parts. First is model-based transfer approaches. Second is data-based transfer approach. In terms of model-based transfer, it can be further break down into with multilingual corpus and with parallel corpus approaches. In terms of data transfer, there are also approaches based on machine translation or code switch data augmentation approach. In the next slides, I will pick some of the representative works to introduce the approaches details. These approaches could also be mapped to the method hierarchy tree introduced earlier by Daxin. Most of the methods belong to the contextual embedding methods highlighted in the yellow color, either using the parallel corpus for training or without the need for parallel corpus. I will give more details in later slides. Okay, so first work is called Multilingual Sentence Encoder, which is actually a baseline method introduced in the original XNI dataset paper. It leverages parallel corpus for sentence embedding alignment for cross-lingual transfer. It can consist of three methods or steps. First, we can train a natural language inference English encoder and a classifier on top. The architecture is shown in Figure A. Both premise and hypothesis are sent to English encoder to get the semantic representations. Then these representations are further concatenated and sent to a classifier to classify into the target labels, which are entailment, neutral, and contradiction. And the second step is once we have this non-EN classifier, we can first train a non-EN encoder, such as Spanish encoder, by aligning the semantic relationship of the English language encoder and Spanish encoder. Specifically, parallel sentences in two languages are sent to the two encoders, and the alignment loss function is leveraged for model optimization. Thirdly, the Spanish encoder is used to fine-tune on the translate Spanish NI training data to obtain the final model. In this way, the model is able to transfer to other languages. Another very strong baseline is multilingual BERT. As we know, pre-trained transformer models have greatly boosted the performance of numerous NLP tasks by large-scale unsupervised language model pre-training. In terms of cross-lingual setting, large-scale pre-trained models can also present very promising results. So in these slides, I'd like to introduce the multilingual BERT work first, which also shows very quite promising results in XNI benchmark. To adapt to the natural language inference task, multilingual BERT adopts a very interesting strategy by transforming the text pair problem into a single text classification problem. To be specific, the premise and hypothesis are concatenated into one single text input and feed forward to pre-trained transformer models to get the semantic representations. Then, on top of the semantic representation, such as a CLS token, a multi-classification head is used to map to the target labels. The benefit of this approach not only lies in the method simplicity, but also fully leverage the multi-head self-attention mechanism to perform premise and hypothesis self-attention, but also cross-attention between premise and hypothesis. In terms of pre-training, multilingual BERT is trained using the same architecture and training scheme with the monolingual BERT, using mask language model and next sentence prediction objectives. The Wikipedia pages in 104 languages are leveraged for mask language model pre-training using 110K shared BP vocabulary. One thing to mention is that even without parallel corpus, multilingual BERT still achieves very decent cross-lingual transfer results in zero-shot setting on the XNI tasks. To further enhance cross-lingual transfer performance, parallel corpus can be one method to leverage during the pre-training stage of language models for better alignment across different languages. XLM, cross-lingual language model pre-training work, is the first cross-lingual pre-training model to leverage parallel corpus for pre-training. Specifically, it introduced a new task called translation language model. You can see the task in the figure here. It introduced a new task called translation language model. To be specific, given a parallel sentence pair, this work performs random token level masking in the input sentence pairs. Then the model is encouraged to recover the mask tokens by considering not only the English context, but also the parallel context. In this way, better alignment across different languages could be achieved for the pre-trained language model. From the results, we can see that by adding parallel corpus for translation language model task per training, XLM model is able to outperform multilingual BERT and the version of XLM model using mask language model objective only with a very large margin. This proves that leveraging parallel corpus for language alignment could boost cross-lingual language transfer. Our group also has a cross-lingual pre-training work called Encoder, which leverages parallel corpus for alignment pre-training. Similar to XLM, mask language model and translation language model are also leveraged in the pre-training stage. Besides, we further introduced two new tasks for better alignment. The first task is called cross-lingual word recovery. Multiply machine translation, we design an attention matrix to represent the source language embeddings by target language limitations. The model is encouraged to recover the original language tokens by using the target language limitations. In this way, this approach could encourage model to better learn fine-grained alignment across different languages. The second approach is called cross-lingual paraphrase. This task targets to decide whether two sentences in different languages are paraphrased or not. By introducing these fine-grained alignment pre-training tasks on parallel corpus, the cross-lingual performance on XNI could be further boosted. From the table below, we can see that in terms of cross-lingual test setting, which is also known as zero-shot setting, which means that the model is only fine-tuned on the English training data only, then directly test on other languages. Encoder achieves better results than both X language model as well as multilingual BERT. In terms of multi-language fine-tuning setting, where all the translate data are combined for joint fine-tuning, this work proves that this method can greatly boost the model performance. Still, Encoder is still able to achieve the best results comparing with XM and the multilingual BERT. These two strong baseline rules. Different with using parallel corpus for explicit alignment across different languages, XM Roberta tries to prove another direction for better cross-lingual transfer by adding more monolingual training data and also training a bigger model. To be specific, XMR only leverages mask language model, but pre-trains on much bigger corpus covering 100 languages than multilingual BERT. From the figure below, x-axis denotes languages, which covers about 100 languages, while y-axis denotes dataset size in gigabytes. Compared with the data used for multilingual BERT, the training data for XMR, which is called CC100, is about 100 times bigger than the training data used for multilingual BERT. Another difference is that XMR uses sentence piece for tokenization instead of the BP method used by multilingual BERT. The results are also quite promising. XMR large, which is 24-layer transform model, is able to achieve the new SOTA results on XNI task across all language settings. This proves that adding more training data and a bigger model could further boost the cross-lingual transfer performance, even without usage of parallel corpus for alignment. Despite the promising results of XMR, we may wonder a question: are parallel corpus still needed for cross-lingual transfer? The answer is yes. InfoXM is a pre-training work built on top of XMR by further leveraging parallel corpus for better language alignment. Specifically, 3 pre-training tasks are used: multilingual mask language model, translation language model, and cross-lingual contrast learning. So as I shared earlier already about the mask language model and the translation language model, in this work, cross-lingual contrast learning is a new task, which maximize sequence-level mutual information between translation pairs, which are regarded as cross-lingual views of the same meaning. The momentum contrast is employed for implementation. The new task further encouraged language model to learn language-agnostic limitations for better cross-lingual transfer. From the results, we can see that InfoXM achieves new total results compared with XMR, also other baseline methods like XM, Encoder, and Multilingual BERT, which prove the value of additional value actually of using parallel corpus for cross-lingual transfer. Besides of improvement and innovations during the pre-training stage, another line of data transfer work is to improve the alignment during fine-tuning stage. For example, a representative work is code switch data augmentation. The idea is that if the model is truly universal, it should be able to recognize this code switch sentence, since the model only focuses on semantic meaning instead of the language characteristics. So here's the process to construct this training data. First, given the original training data, say like in English, we randomly sum some sentences. And second, then for the select sentences, some tokens are randomly selected and replaced with a token with the same meanings in other languages. In this way, multilingual code switch training data can be constructed automatically. By applying code switch augmentation on top of pre-trained models like Multilingual BERT and the X language model, the performance had a big boost across all languages of XNI, which proves the effectiveness of this code switch data transfer method. Okay, so here are some key takeaways of the cross-lingual natural language inference. First, parallel corpus helps better language transfer, which are proved by Encoder, XM, and InfoXM work. Second, bigger model leads to better performance, which is proved by XMR, by showing that 24-layer transformer model is able to outperform 12-layer or 16-layer models. Thirdly, large data leads to better performance, which is also proved by XMR by using about 100 times larger datasets than previous works. Okay, next, let me hand over to my colleague Xiubo to introduce the cross-lingual information retrieval. Thanks.
Hello, everyone. So I'm going to talk about the cross-lingual semantic retrieval task. This is the outline. So first, I will give a brief introduction to the cross-lingual semantic retrieval task. And then I will talk about models used for it, including two basic model architectures and some advanced approaches. Finally, I will talk about some data augmentation approaches. So the cross-lingual semantic retrieval task is defined as follows. Given a sentence in one language, we aim to retrieve relevant sentences from a large candidate pool in other languages. Here, two relevant sentences means that they share the same semantic, but they are expressed in different languages. So that cross-lingual semantic retrieval task can be applied in many scenarios. For example, the Paracorbus Mining, cross-lingual question retrieval, and so on. So let's take Paracorbus Mining as an example. It is used in machine translation. So in machine translation, high-quality training data is usually critical for the model training. So Paracorbus Mining aims to mine large volume of such parallel sentences from two monolingual corpus. To achieve that, it needs to first retrieve candidate sentences from one languages for sentences in other languages. And such a retrieval process can be viewed as a cross-lingual semantic retrieval task. So similar to other cross-lingual tasks, it needs to align embeddings of different languages into one common space. Since in the retrieval process, the query sentences and the candidate sentences are in different languages. So therefore, we need to map them into one common space and then conduct the retrieval. But different from other cross-lingual tasks, such as the natural language inference task, it is not feasible to conduct full interaction between the input sentences. Here, full introduction, we means that like the token by token attention interaction. The reason is the retrieved candidate pool is usually very large. So the retrieval efficiency is critical. So a feasible solution is shown in this figure, where we usually first pre-encoded all targeted sentences into embeddings and then build index for them. And then for a given given a source language sentence, we first encode them into an embedding, and then use the embedding as a query to conduct approximate nearest neighbor search from those pre-encoded embedding sets. And then we get the retrieved results. So in the remaining time, I will merely focus on the encoder part, which aims to generate language-independent embeddings for sentences of different languages. But in the training process, it can be viewed as a text classification problem, which takes two sentences of different languages as input, and it outputs the similarity between these input sentences. Now let's talk about the models used for the cross-lingual semantic retrieval task. Basically, there are two popular model architectures, namely the dual encoder model and the neural machine translation-based model. I will talk about these two models in detail next. Let's first look at the dual encoder model. So given a sentence pair of X and Y, it first encodes these two sentences separately into two embeddings, U and V. And then the similarity between X and Y is evaluated as the similarity between U and V. And in the training process, the learning goal is to maximize the similarity between parallel sentence pairs while minimize those sampled negative sentence pairs. So we can see that when the input sentence pairs X and Y are in different languages, such training objective will try to map these two languages into one common space explicitly in the learning goal. As the encoder, there are many choices. For example, Guo and al. Propose to use a deep averaging networks, which first get sentence embeddings by conducting pooling on diagram embeddings and word embeddings, and then they apply a feed-forward network on top of it. Another choice is the transformers, and recently dual transformer models is becoming more and more popular in the multilingual sentence embedding. So here are more details about the model training. So given a sentence pair of X and Y, which are translations of each other, then we define the probability of Y is a translation of X by applying a softmax over the matched sentence pairs and those negative sentence pairs. Here, the negative sentence pairs are composed of X and other sentences in the same language as Y. But the problem is that the space of negative sentence pairs is usually very large. And to reduce the time complexity, it is usually approximated by this probability, which ranks only K negative sentence pairs. So a straightforward solution to get the K negative sentence pairs is by random sampling. But that might lead to the model only focus on whether the input two sentences share the same topic, since it's very likely that those randomly sampled sentence pairs are quite irrelevant with each other, and they even do not talk about the same topic. So to tackle this problem, Gu and al. propose to use hard negatives in the training data. The idea is to they try to identify those sentence pairs, those negative sentence pairs, which are similar, which might semantically similar to each other, but they are not exactly translation of each other. So specifically, they first train a baseline model with randomly sampled negatives, and then they select those negatives which get high relevance scores according to the baseline model. So such hard negatives enforces the model to further distinguish sentence pairs which might talk about the same topic, but they are not exact translations of each other. So another popular used model architecture is the neural machine translation model, which is basically an encoder-decoder model. Artex and Swank propose to encode multilingual sentences using a single encoder-decoder model. So this figure shows the architecture. So given an input sentence, it first apply context embedding using a bias TM, and then get sentence embedding by conducting max pooling. And given the embedding of input sentence and a target language ID, it then employs a LSTM as an encoder to generate translated sentences. So the key idea of getting multilingual sentence embedding is that the training data consists of many different language pairs, as shown in this figure. For example, translating from German, French, Russian, and other sentences to other languages to one or more common target languages. So learning a single encoder-decoder model from such training data, then the encoder part will encode all these source languages into one common space. Since they are translated to common target languages. And such language alignment is achieved implicitly, since we didn't explicitly maximizing the similarity between them. But if input sentence is translated to other languages in the training data, such required training data is too large, and the training process will be very time consuming. So to tackle this problem, Artex and Swank propose to use only 2 target languages, that is English and Spanish. Both of them are popular languages, and it is relatively easy to get translations between other source languages and these 2 target languages. They use almost 100 source languages in their training data and learn a single encoder-decoder model. And given the learned model, in inference, we only need the encoder part. That is, we get language-independent representation for each sentence using this encoder, and then conduct retrieval according to the embeddings. Here is a list of all the 93 source languages they use. And they also test the cross-lingual semantic retrieval using between English sentences and all these source languages. And the test is bidirectional. That is, they retrieve all these source languages use English sentence, and they retrieve English sentence from these source languages. So this table, we summarize and get that 37 languages get below 5% error rate. And only 15 languages, we get the error rate about 50%. So these results demonstrate that such multilingual sentence embedding approach is effective for the cross-lingual retrieval task. To summarize, there are mainly 2 popular model architectures used: the dual encoder model and the new machine translation model. Both of them require Paracorbus data for model training, and they align sentences of different languages into a common space for the retrieval process. But the dual encoder model conducted the language alignment explicitly in their model training. That is, they directly maximizing the alignment between 2 languages. While the new machine translation model can get the model alignment implicitly. So when multiple source languages are translated to 1 or more common target languages, then the encoder part will encode all these source languages into a common space. And such alignment among multiple languages are achieved implicitly. Let's talk about some advanced approaches. I will mainly talk about 2 directions, that is, better loss function for model training and a better scoring function for inference. So Yang et al. Proposed to improve the training process with a addictive margin and a bidirectional encoder-decoder. Let's first look at the addictive margin. So the goal of this margin is to structure the embedding of sentences to be more compact. That is, This is shown in this figure that compared to the original embedding space, where each point represent a sentence, as different shapes represent different topic and different categories, different semantic. So compared to the original embeddings, the new embedding space with additive margin structures the space more compact. That is, sentences of same semantic are closer to each other, and the margin between them and those unsimilar sentences are large. So this is achieved by an additive margin on the scoring of positive sentence pairs. Here, xi and yi is a pair of parallel sentence, and their score in the model is extended by a margin m. And here these are scores for negative sentence pairs, and they stay unchanged. And this equation shows the updated loss function. So using this new loss function in the training process, it enforces the model, the scoring function, to score those matched sentence pairs to be close to each other as close as possible, and it naturally distinguishes these sentences to other negative sentences nearby. In addition, Yan also proposed a bidirectional dual encoder to fully exploit the training data. The idea is, given a sentence pair, it computes two probability. That is, given a sentence pair of x and y, it computes the probability of y is a translation of x, and the probability of x is a translation of y. So the difference of these two probability lies in the negative samples. Here, for the probability of y is a translation of x, the negative sentences, the negative sentence pairs are constructed by using x and other sentences in Y language. So in contrast, in this probability, the negative sentence pairs are contrasted by Y and other sentences in X. So such bidirectional probabilities using negative samples for both languages, and further, therefore, they can fully exploit the training data. Here is the experimental results on the cross-lingual semantic retrieval task. So we can see that compared to the vanilla dual encoder, the bidirectional dual encoder can increase the precision of this task. And adding an additive margin in the loss function further improves the performance. So that's the model training improvement part. So let's look at the improvement in the inference phase. So given a trained multilingual sentence embedding model, a straightforward strategy for Paracorbus mining is first conduct nearest neighbor search, and then filter the retrieved results with a hard threshold. But the problem is that similarities of different sentence pairs are not always consistent. So it might not be easy to find a global consistent threshold for the filtering. Let's look at the examples in this table. So here, all these false English sentences are negative sentences for this French sentence, but they have high scores with respect to their embedding. In contrast, in this English sentence, the first English sentence is a good translation of this French sentence. However, its score is lower than all these negative sentence pairs. So in this case, we cannot find a good threshold to filter irrelevant sentence pairs. And if we want to filter out these negative sentence pairs, we need to set a threshold higher than 0.9, 0.8. But that will filter out these good translation pairs. So to tackle this problem, Atex and Swank propose a margin-based scoring function for filtering. The idea is that in order to evaluate the score between X and Y, it not only considers the similarity between their embeddings, but also consider two additional scores. That is, the similarity between X and its nearest neighbors, and the similarity between Y and its nearest neighbors. So if a sentence X is close to its nearest neighbors, and then the similarity between X and its nearest neighbors is high, then the similarity between X and Y will be reduced. So such approach will reduce the scores of those harmless sentences. That is, those sentences which are close to many of its neighbors. So the intuition can also be illustrated in this example. So if the sentence is close to only its nearest neighbor, while has lower similarity to other neighbors, then the closest neighbor is likely to be a good parallel sentence. However, if a sentence's nearest neighbors all have high relevance scores, then it is likely that these neighbors are not good parallel sentences. So they also improve this. They also test the effectiveness of such inference score on the cross-lingual semantic retrieval task on two data sets. And here we can see that such simple scoring function get a very significant improvement for cross-lingual semantic retrieval. And as for the margin functions, there are many choices. So Atex and Swank compare three different variants. The absolute margin, which is a special case that is only it reduces to the cosine similarity. And the distance margin between A and B equals to A minus B. The ratio margin between A and B is the ratio between A and B. So here is the comparison between these three margin functions. We can see that both distance function and ratio function outperform the simple cosine similarity by a large margin, that is more than 10%. And the ratio margin is slightly better than distance margin, although the difference is not very large. So that's the improvement for the model part. Now let's talk about the data augmentation approaches. So the motivation for such direction is that most previous works usually require parallel data for the model training, but such data is not easy to get, especially for those low resource languages. Meanwhile, we usually have a large volume of monolingual data. So the goal of this research direction is to generate multilingual sentence embeddings with limited, even no parallel data when we have monolingual data. So Singlet et al. Proposed to learn high quality multilingual sentence embedding with a limited set of paracorpus. They employ a multitask learning approach, that is, which includes a multilingual skipgram for word embedding and cross-lingual sentence similarity task. And these two tasks are joint learning via shared word embedding. Now let's take a close look at. Let's first look at the multilingual scriptgram. So this is an extension of monolingual scriptgram. Its training data consists of two types of data, that is monolingual context word pairs and cross-lingual context word pairs. The monolingual pairs try to predict words according to context from monolingual data, that is from language 1 to language 1 or from language 1 to language 2. And this data can be sampled from both monolingual data and paracorpus data. So the cross-lingual context word pairs try to predict words in one language according to context in another language. For example, to predict language 2 word according to language 1 context and vice versa. And such data is sampled from Paracorpus. This figure illustrates the monolingual pair and the cross-lingual pair. Here, the blue links shows the monolingual pairs. That is, the word and the context are from the same language. And the red links shows the cross-lingual pairs. The word and the context are in different languages. So by leveraging both monolingual and cross-lingual pairs, we can achieve two goals. First, the large volume of monolingual pairs help to learn embeddings of a large size of tokens, while at the same time, the cross-lingual pairs help to align embeddings between different languages. So learning from such data will help to generate a language-independent embeddings of large volume of tokens. And they also use a dual encoder for sentence similarity task. Specifically, the sentence embedding is based on the word embedding, which is a shared layer with the multilingual multilingual skipgram. And based on the word embedding, they first apply a bias TM layer and then conduct average pooling to get the sentence embedding. And the similarity between two sentence embedding is optimized in the training process. So the multilingual skipgram and the cross-lingual sentence similarity models are trained jointly with the shared word embedding so that they can inform each other through this embedding. So here is some experimental results. Here the different rows different columns represent different sizes of paradata. And the first column represents no monolingual data. We can see that if we reduce the size of paradata, the performance drops quickly. And here different rows represent using different sizes of monolingual data. We can see that for any given size of paradata, if we compare vertically, using monolingual data always can improve the performance. This shows the effectiveness of this multitask learning approach. And here is another case study. Here is the nearest neighbors of 3 English words in different languages. So the blue colors represent words that exist in Paracorbus, while the red color represent words that only exist in monolingual corpus. So we can see that although there are some words that only exist in monolingual corpus, such multitask learning approach can still align them in the same embedding space. Okay, that's the work using both monolingual and para data. So to further reduce the reliance on the para data, so some researchers are also trying to use only monolingual data. So try and conduct some analysis for a multilingual model, a multilingual pre-trained model, and BAT. So they conduct cross-lingual semantic retrieval for different pairs of languages with the model without any fine-tuning, and find that even use such model can get a relatively good retrieval accuracy, as shown in this figure. And they further find that they can get a big improvement, that is 27% of accuracy on all languages when they just fine-tune the model on Japanese English para data. So such observation motivates them that to think that first, MBAT is a good starting point for cross-lingual retrieval. Second, so this model can be further improved by para data mined from the model itself. So based on this thinking, they propose a iterative approach which use the MBAT model as a starting point to mine Paracorpus from monolingual data. Then the pseudo para data is fed into a multilingual machine translation training process to get a new sequence-to-sequence model. And this new model is then further used to mine pseudo para data. And this iteration goes on. Finally, given this trained sequence-to-sequence model, it can be used in many downstream tasks, such as machine translation or the cross-lingual sentence retrieval task. So here is the results. We can see that only after 2 to 3 iterations, the retrieval accuracy is significantly increased. This demonstrates that such iteratively approach can get a good performance for the cross-lingual semantic retrieval task. Of course, however, there is still a gap between the unsupervised and supervised approach. So this is a good research direction that using only monolingual data to mine for model training or multilingual sentence retrieval. So to summarize, here is some key takeaways. So first, we talk about 2 popular model architectures used for the cross-lingual semantic retrieval task, including the dual encoder model, which achieves explicit language alignment, and the neural machine translation model, which achieves implicit language alignment. And then we talk about several advanced approaches, including improved model training by additive margin, improve inference by margin-based scoring, and enhance those low-resource languages' performance by leveraging monolingual data. Okay, that's all of my part. And next, Ming will talk about the machine reading comprehension task. Thank you.
Hello everyone, I'm Ming from NLP Group, STC at Microsoft. Nice to meet you online. In the previous sessions, Linjun and Xiubo have introduced two applications of the test classification. In this session, I will talk about sequence labeling task, mainly taking the machine reading comprehension as an example. Here is the outline. Firstly, to recap, I will give a brief overview of the sequence labeling applications. Then, taking the cross-lingual Mrc task as an example, we will go through the three aspects together, including the task definition and the benchmark datasets, the baseline approaches, and the related challenges. And to address these challenges, the advanced approaches will be introduced accordingly. Finally, the key takeaways and more thinking of the ongoing work will be summarized. Sequence labeling is also belonging to NLU applications. Similar to the test classification, the task of sequence labeling can also be divided into two scenarios depending on the input, including the single text input and the text pair input. Here are some example tasks for the both scenarios. For single text input, one example is the name entity recognition, or short for NER. Traditional NER only consider person, organization, and location as entities. But depending on the requirement of the applications, we can expand the set of target entities. Here is one example to trigger a flight status answer card on the Bing search engine. Given a user query, we need to label various entities, also called slots, such as the departure, airport, arrival, airport, and the airline company, and so on. For the test pair input, the example here is the extractive machine reading comprehension, where for each instance, there are a question and a passage. Then the problem is to label the answer span with respect to the given question within the given passage. Here's an example from Bing. If you ask, when is Web Conference 2021? The search engine will highlight the answer in the relevant passage to this question, which is April 19 to April 23, 2021. In the rest part of this session, we will take Mrc task as an example to introduce the language scaling approaches. Before 2020, there were few benchmark datasets for cross-lingual Mrc. There were mainly three datasets published in 2020, including ML-Q&A, Tidy Q&A, and XSquad. Here are examples from ML-Q&A, which are commonly used in related work. For each instance in ML-Q&A, it contains a question and a passage, and the goal is to extract the precise answer span from the passage, like the orange highlighted phrases here. ML-Q&A contains Q&A instance in 7 languages, including English, Arabic, German, Spanish, Hindi, Vietnamese, and simplified Chinese. The typical experiment setting with this dataset is for the model training, only English label data is used without other language-specific label data. Then after training, directly test the model on non-English language test set. Similar to the classification tasks introduced in the previous sessions, there are two baseline approaches on top of the cross-lingual pre-trained model. One is zero-shot training, which only uses English labeled data to fine-tune the cross-lingual pre-trained model and directly test on the non-English languages. The other is translation training, which translate the English label data to the target languages, and then leverage only translated data or the mixed English and translated data for fine-tuning. With the powerful transfer capability of the latest cross-lingual pre-trained model, the zero-shot and translation training already show very good results in the classification task, like XNLI introduced by Lingjun previously. However, there are clear challenges for Mrc task due to the characteristics of the sequence labeling task. There are mainly four challenges using these baseline approaches for cross-lingual Mrc task. The first challenge is the language transfer capability of the cross-lingual pre-trained model for classification task versus sequence labeling task. Here is one intuitive analysis between Mrc task and NLI task. They fine-tuned the cross-lingual pre-trained model with the English label data for Mrc and NLI task respectively, and then test on other languages directly. The table shows that the gap between the target languages and English on the Mrc task is significantly larger than the sentence level classification task like NLI. So for the phrase boundary task like Mrc, we can see that the better semantic alignment among different languages is required. The second and third challenges are regarding the machine translation quality. For Mrc task, when translate English labeled data to target languages, we will translate both the question and the long passage. So the translated noise will be more likely to be expanded, thus influence the original correlation between the question and the passages. Besides of the question and passage translation, for Mrc, we also need to translate the answer span to the target languages. Usually, the passage and answer span will be translated separately, so it's challenging for the answer span alignment in the translated passage. Here is one example. For the question, where is the Earth during the full moon? The correct answer span is a highlighted phrase with a green color in this passage. After translation for this passage and the answer span, respectively, we could see that the translated answer span has misalignment with a correct span in the German passage. Since Mrc task requires to extract the direct answer span from the passage, it is critical for the precise answer boundary detection. According to the error analysis on the ML Q&A for the zero-shot cross-lingual Mrc model, the major errors come from the answer span partially overlap with the golden span, like the two cases on the right. For example, the ground truth for the first case is King David. However, our model predicts David together with some redundant phrases as the result. The ground truth for the second case is 50 to 100 milligram. However, our model predicts a partial span 100 milligram as a result. Taking the Spanish and German as example, the partial overlap of the golden span accounts for as high as 66 and 75% in all model prediction errors respectively. So it's important to enhance the answer boundary detection capability of the cross-lingual Mrc models. To summarize, there are three major types of challenges of the baseline approach for cross-lingual Mrc task, including the insufficient semantic transfer capability across languages, the machine translation data quality issues, and the insufficient answer span boundary detection capability. There are a series of recent works to address these challenges, In the following, we select 7 representative work for detailed introduction. To echo the language scaling approaches introduced by Daxing in the first part, these advanced approaches for cross-lingual MRC belong to the contextual embedding models with or without parallel data. Firstly, let's look at the representative works to further enhance the semantic transfer capability for the phrase boundary task. The first work proposed a new task called Mix MRC Task with the machine translation data to enhance the semantic transfer. Here's a graph to show the Mix MRC data generation. For the English question passage pair, they will translate them into the target language, like German. Instead of directly use the German question, German passage, they further mix them to get the question passage pairs in mixed languages. For example, German question with English passage, English question with German passage, etc. The intuition to design this mixed MRC task is that for our human, if someone truly understands the 2 languages, they could well perform the more challenging MRC task in the mixed languages. So with infusing the challenging mixed MRC task for model training, we could expect to further enhance the transfer capability of the cross-lingual MRC model, since it could do a more difficult task. This mixed MRC task is infused as one auxiliary task of the main MRC task in the fine-tuning stage. Compared with the zero-shot training, we could see that there are decent EM and F1 metric gains for Spanish and German on the MLQ&A, no matter using Multilingual BERT or XLM as the backbone model for the fine-tuning. The dual BERT was proposed on EMLP 2019 to make use of the representations learned from the source language, say English, to help the target language understanding. There are 2 encoders in both source language and target language. Specifically, it injects the information from the source language into the decoder of the target language to help boost the model performance on the target language. From the results of the right table, we can see that the dual BERT achieves good gains on the cross-lingual MRC tasks. Compared with the baseline methods, either use the target language-specific BERT model for fine-tuning or use the multilingual BERT for fine-tuning. Since the dual BERT injects information from the source language into the final decoder of the target language, which is kind of the later stage of model training, it doesn't leverage the deep intrinsic relations between 2 languages. To further address this, another dual encoder-based model called filter is proposed, which leverages the translated data to enhance the fusion in early model training stages between the source and target languages for the better cross-lingual language understanding. As illustrated in Figure C, filter firstly encodes a translated language pair separately in the first M shallow layers, then performs cross-lingual fusion between the languages in the intermediate key layers, and finally encodes the language-specific representations in the deeper layers. Compared with the translation tree baseline in the Figure A, filter learns the additional cross-lingual alignment across different languages. Furthermore, compared to simply concatenating the translated language pair as input, like Figure B, filter strikes a better measured balance between the cross-lingual fusion and the individual language representation learning. From the results, we can see that filter achieves the best result in the cross-lingual MRC benchmarks, comparing with the multilingual BERT, XLM, Robota baseline methods, either use zero-shot training or the translation train. The fourth work, published on the WWW 2021, proposed an adversary training method to bring the embeddings of different languages closer to each other to achieve better cross-lingual transfer. Specifically, in addition to the normal Q&A loss, an adversary loss is introduced to make the embedding across different language closer, which try to fool a language classification discriminator. From the result, we can see that the adversary training brings significant gains across all language on the ML Q&A dataset, which shows that the better alignment through the multilingual adversary training could bring the better language transfer capability. As we mentioned at the beginning, the MT data quality also brings challenges for the cross-lingual Mrc task, since both the query and long passage need to be translated, which will bring the expanded noise. It's also challenging for the alignment of the translated answer span with the translated passage. 3 representative works will be introduced to address the MT data quality issue. For Mrc data translation, since passage and answer span are usually translated separately, it's very likely that the answer spans after translation may not exist in the translated passage or have some boundary errors. To address this challenge, the work published on the Out NLP 2019 proposed 3 approaches for the answer span alignment after translation. The first approach is called Simply Match. They calculate the character level test overlap, say the F1 score, between the translated answer span and the arbitrary sliding windows in the target passage. Then use the sliding window candidates with the best F1 score as their final answer span. The second approach is called answer aligner. Like the middle graph of Figure 1, where they feed the translated answer span and the target passages into a bot model. The model will learn the semantic relations between them and generate the improved answer span for the target language. The third approach is called answer verifier, like the rightmost graph of the Figure 1. On top of the answer aligner approach, it further infuses the query text in the target language into the BERT model, and verify the translated answer span correctness and generate the improved answer span for the target language. Here are the experimental results using different alignment approaches. Without using any answer span alignment approaches, we could see that all the metrics are pretty low. By using Simply Match, answer aligner, answer verifier, the EM and FN scores get a significant boost. Among the 3 alignment approaches, the answer verifier achieves the best result. It's kind of aligned with our intuition, since all the important information in target language, including question, passage, and the translated answer span, are used for the verification and the span improvement. To further reduce the negative impact of the noisy MT data, a novel language branch knowledge distillation was proposed in the work published on the Calling 2020. The core idea is to leverage multiple teacher models for kind of a smart assembling to overcome the MT noise. To train the multiple teacher models, they leverage the machine translation to generate the so-called language branch Mrc datasets. To be specific, they firstly translate the English question passage pairs into different target languages like Spanish and German. Then they group the question passage pairs according to the passage language. For example, for an English passage, it could be paired with its English question and also the translated Spanish and German questions. With this approach, they build up the language branch MRC datasets and leverage these language branch datasets to train multiple language branch teacher models based on the cross-lingual pre-trained model. These language branch teacher models could predict the soft labels for all the training data respectively. The authors also design a smart model score assembling method to weighted sum up the predictor scores by the teacher models, and finally leverage the soft labeling data to distill a teacher model. For the results on the ML-Q&A and SQuad datasets, these language branch approaches all achieve the SOTA result. We assemble the scores by multiple teacher models in the previous language branch MRC work. Each teacher model is using a same weight for all cases, which is kind of static. However, for different cases, the performance of a teacher model are likely to be different. Thus, the optimal approach is to assign different weights for each teacher model at instance level in order to get the best assembled soft labels. With this motivation, our team's work in WWW' 2021 proposed to leverage the reinforcement learning for the multi-teacher selection at instance level. Specifically, an agent is introduced to take action to decide whether to select each teacher model or not. Once the teacher model are selected, the assembled soft labels will be used to optimize the student model. After training the student model, we will evaluate on the golden label test set. The metric is treated as rewards to further optimize the agent to make a better decision in the next iteration. In this way, the method is able to select the most suitable teachers at instance level. Here are the comparison results. Compared with the static assembling approach, the reinforcement learning-based teacher selection at instance level achieved significant gains. The papers also studied 3 different reward functions by considering different methods to calculate the student model performance, including using the cross-entropy, MSE loss, or the performance on the depth set instead of the training set. Across all the reward calculation settings, the RL-based teacher selection at instance level achieved the best result. The third challenge is how to further enhance the answer span boundary detection for the cross-lingual MRC model prediction. I will introduce 2 representative works to address this challenge. Since the answer boundary extracted by MRC models are mostly entities or meaningful phrases, the first work published on the ACL 2020 proposed a scalable approach to mine the large-scale knowledge data from the web pages and leverage this knowledge data to design a language-agnostic knowledge masking task, short for LAKM, to introduce the language-specific boundary prior knowledge into the model. Here, the knowledge data is not limited to the entities. Instead, it includes all kinds of meaningful phrases. Given a user query, the authors leverage the search engine to get the top-ranked URLs and use the URL titles to firstly extract the commonly occurred phrases as the candidates. Then design lots of useful features to finally decide the truly meaningful phrases. This knowledge data mining process is language agnostic. With the knowledge data in various of languages, the authors design a knowledge masking task as an auxiliary task of the main Mrc task in the fine-tuning stage. Here are the experimental results on ML-Q&A and MT-Q&A benchmark. We could see that by adding the LAKM task, the EM and F1 scores have significant improvement across different languages. Besides of knowledge infusion, the other work published on the Wisdom 2021 proposed a two-stage approach for the boundary refinement, which is inspired by how we humans write articles. Let's look at the leftmost case for the main idea. Given a passage and a question, firstly, use a base module to get the draft answer span, which probably have some boundary detection errors. Then leverage a calibration module to further refine the boundary and get the final calibrated answer. The whole process is called calibration network. The right graph shows the model architecture, which includes a base module and a calibration module. The base module could be whatever MRC model we already have. The challenge is that how to collect the training data for the calibration module training, especially for those non-English languages. To address this challenge, this work leverages the wiki document to synthesize large-scale training data in multiple languages and design a novel phrase boundary recovery task to pre-train the calibration module. To be specific, there are lots of hyperlinks in wiki for the meaningful phrases or entities. The authors extracted the linked phrases as a golden answer span and gobbled them by some operations like delete, add, or shift some words to synthesize the noisy answer spans. Then for the phrase boundary recover task, it will take these noisy answer spans as input and the original hyperlinked phrases as ground truth for the denoisy pre-training. According to the results on ML-Q&A, the average F1 score and EM score across 7 languages have significant gains by adding the calibration module. Since the calibration module is orthogonal to all the existing MRC models, so it could be easily added on top of all previous MRC work to bring the actual gains. Here are the key takeaways. Mrc Task is more challenging in language scaling, and the baseline approaches don't work sufficiently well due to 3 major challenges. Firstly, to address the insufficient transfer capability of the cross-lingual pre-trained model. By leveraging the machine translation data, the new mixed Mrc Task, dual encoder-based model, and the multilingual adversary training approaches are proposed to enhance the semantic transfer capability across different languages. Secondly, to reduce the negative impact of the machine translation data quality, the back translation plus verification is proposed to improve the answer span alignment after machine translation. Multiple teacher models trained with the language branch machine translation data are used for the soft label assembly to reduce the MT noise. Besides, the reinforcement learning-based best teacher selection at the instance level could further reduce noise for better student model training. Thirdly, to enhance the answer span boundary detection, the new LAKM task is designed to infuse the language-specific boundary prior knowledge during the MRC model training. Besides, the calibration network is proposed to add a new module on top of the existing MRC model to refine the answer span boundary. Beyond cross-lingual pre-trained model, plus the machine translation data as augmentation, there are more ongoing work to further address the cross-lingual MRC challenges. In most cases of the real production, like Bing search engine, it is relatively easy to get the large-scale, language-specific, and labeled data. For example, the real question passage pairs in specific languages. Then some semi-supervised learning approach, like self-learning, could be used for the unsuspect prediction and the model iterative improvement. In some cases, due to the data access limitation, the available labeling data and language-specific unlabeled data are only a few. We may leverage the sequence-to-sequence model and a few seed data to synthesize more question, passage, and unsuspect triples for the data augmentation. We will cover more technical details of this ongoing work in our future tutorials. Okay, that's all for the application part. Thanks for your attention. I will hand over to Daxin for the future directions.
Okay, as the last part of this tutorial, I would like to share my thinking about the future directions for language scaling. Actually, these are some questions in my mind for a long time. So I wish more people are also interested in these questions and explore more solutions in the future. So the first question is, how can we systematically integrate more linguistic knowledge into language scaling? We know that languages are very different in morphology, syntax, and semantics. So the essential problem for language scaling is to bridge the gap between languages in all these linguistic features. Although the current approach of model transfer and data transfer have proved effective in many cases, the empirical study also showed that the performance of transferred models may still not be very satisfying, especially when the target language is distant from the source language or the resource for the target language is extremely low. So in order to address these challenges, we may consider integrating linguistic knowledge into our data-driven approach. For example, the efforts of universal pause tagging and universal dependency parsing want to set up standard syntax analysis schemas across all languages. So in this way, all languages can represent their syntactic structure using a uniform schema. And these efforts can definitely help to universalize the language representations. And at the same time, more and more topological databases are available now, such as the World Atlas of Languages, Foible, Ethnologue, Glottalog, and so on. However, currently, we only see some early works using these databases to measure the distance between languages. And some works further use the measured distance to select the intermediate transfer languages. We still look forward to systematic methods that integrate linguistic knowledge into the transfer approaches. Then the second direction is the best practice to train multilingual models. As we explained in previous slides, in order to save the maintenance cost in practice, we usually build a universal model to support multiple languages. Right? Then we got a series of questions about training this universal model. For example, when transferring from the source language to multiple targeted languages, the model tends to overfit on the new data, but loses the useful information learned from the earlier data. So this problem is sometimes referred to as the catastrophic forgetting. So one question is, how can we deal with this forgetting effect? Moreover, linguistic studies have grouped languages into hierarchical families. So this picture shows example for the family of Proto-Indo-European languages. Intuitively, it is easier for languages in the same family to transfer the knowledge because they share more topological features. Therefore, it makes more sense to put languages in the same family into a single universal model. However, there are very few studies to verify the effectiveness of this assumption at a large scale. And even if this assumption is true, it is still not clear how to choose the level in this hierarchical family tree to group the languages in the same model. And another question is about how to measure the capacity of models versus the size of languages. But we can imagine that when we put more languages into a single universal model, it needs more parameters to capture the variations in the data. Right? However, we still don't know how to measure the model capacity or the language size so that we can determine the best combination of languages in the same model. So we hope that there will be more theoretical or empirical studies to give us answers or guidance to these questions. And the third direction is more from in industrial perspective. For example, in Microsoft, there are many different NLP applications. Then given a specific application, our question is how can we find a recipe to combine various data and various methods to reach the best ROI, that is return over invest. So in this tutorial, we have introduced many language scaling methods. So here we just list several high-level categories, and we know that there are many methods in each category. We should note that the cost to apply different methods has big difference. So some methods need large offline training capacity, while some methods are very expensive for online inference. So when we choose the methods, we should take the cost into consideration. Moreover, different methods require different types of data, such as pre-trained corpus, unlabeled data, tree bank, translated data, parallel data, bilingual dictionary, and so on. So in practice, the extent of difficulty to collect this data is also very different for different languages. Moreover, there may also be some constraints, such as privacy issues or cold start situations, which make certain types of data impossible to collect. So the point here is that it's not as simple to find the best language scaling approach, given a real application in practice. Therefore, for each NLP application, we should consider various practical settings and constraints and figure out the best way to combine the different available data and all kinds of candidate methods to reach the best ROI. And we look forward to more studies in this direction. Okay, that's all for our presentation, and thank you very much for your attention. So the next part will be the QA session.